Hamiltonian operator we've looked at so far is a special case because for a single particle operator, the occupation number states were chosen to be the eigenstates of the Hamiltonian. How would we represent other single particle fermion operators, such as the momentum operator or the position operator, in this annihilation and creation operator formalism? Having a suitable approach for this is practically quite useful. We may need it, for example, if we're to handle the position r in the electric dipole interaction for the form E dot r, where E is the electric field. Similarly, we might need it to handle the momentum in the A dot P interaction, where A is the magnetic vector potential. Now, note that the following argument becomes quite involved, with many steps required to complete the formal proof. This is probably not a proof you will be likely to be required to reproduce, but it's useful to go through it once to see the arguments and the results. This will also help us understand just how this annihilation and creation operator formalism leads to some very simple ways of writing down such quantum mechanics. So here we're going to consider a system with n fermions. In the R, or position representation of an operator, some operator G, and we put an R subscript here to make the point we're talking about this position representation. This could be, for example, the momentum operator. And for a multiple fermion system, then what we would do in our previous way of looking at things, which was perfectly correct, is that we would add all of the operators corresponding to the coordinates of each particle. So if we had n different particles, capital N different particles, and each of them had some set of coordinates, so this is a set of coordinates, r, I, for the ith particle in this list, we would have a separate operator if we're talking about a single particle operator, as we're talking about here. And to get the operator for the entire set of these, we would simply add up all of these single particle operators. They're single particle operators because they're only concerned with one particle at a time. So, as I said, this G with a subscript Ri is the operator for a specific particle. It might, for example, be the momentum operator. That's a good example of a single particle operator. The momentum operator only operates on one set of coordinates at a time. Now, in the annihilation and creation operator formalism, we're going to postulate instead that we can write this operator for all n of the particles in this form. The G of r in here is still the sum over all of the individual operators, just as we wrote previously. But now we have the wave function operator and its Hermitian adjoint inside this integral here to give us our overall operator G. And the wave function operator, we remember, we defined before, for an n-particle system would take this form, where each of these A's and B's and so on corresponds to a single particle state with corresponding wave functions, as in this list here. And we're summing over all the possibilities that we could have here. So this operator overall becomes as we have in the following. As I said, buried inside this G of r is the sum over all of the different possible choices of coordinates, Ri. So that sum we still have here. The 1 over root n, because it comes in twice, gives us 1 over n out the front. We get a list of annihilation operators and single particle wave functions corresponding to each of those single particle states here. And that appears, here's our list of those annihilation operators and the corresponding single particle basis states here. And then also from the adjoint of the wave function operator, we have all of these operators, which become creation operators now because of an adjoint. The order of them is the opposite of the order here because of the adjoint operation as well. And we have to put in different indices. We have A prime here where we had A there, and B prime here where we had B there, and so on. These are different summation indices that we have to use here because we're performing a separate sum inside here. So we've primed all of those. And then we have this integral here, which is still the same integral we would have to have evaluated before, and now it's for one specific particle Ri, because remember we are summing over all of those. That was implicit in here. In this expression then, each of these A's and B's and so on up to n, and each of the A primes and B primes up to n prime, ranges over all the single particle fermion states. And now all the spatial integrals except the one over Ri lead to Kronecker deltas of the form delta k prime k here, forcing A prime equal to A, B prime equal to B, and so on, except for particle I. So this operator here only has coordinates Ri in it, so it only operates really on one of these functions in here, the one with coordinates Ri, and all of the others can just be moved past this operator over to the left, where they can multiply their corresponding complex conjugated versions on the left. So those integrals all lead to 1, except possibly the one where we're left with this g of Ri, a psi of some kind of Ri in here, and a psi star of some kind of Ri over there. Hence, in this expression here that we are left with, where this number here is just the result of this integral, that was the one remaining integral we still had to do from our previous expression, the one associated with coordinates Ri. Now we can use the anti-commutation relation. So bj bk plus bk bj is equal to 0. That's the anti-commutation relation for annihilation operators. To progressively swap this operator from the right to the center, and we can use this anti-commutation relation for the creation operators to progressively swap this operator all the way from the left-hand side here to the center. Each such application of an anti-commutation relation results in a sign change, of course, but there are equal numbers of swaps from the left and from the right, so there is no net sign change in this operation. Hence we have that this operator G has this form, where we have now managed to move these operators into the center, and this list now omits specifically the operator B dagger I1, and this list omits the operator B I2. Now, in practice with any operator, in the end, we're working out its matrix elements. And any two operators with identical matrix elements are equivalent operators. So we consider two possibly different n-fermion basis states. So here are two possibly different n-fermion basis states. And we consider matrix elements of our operator G in this form that we just written down between such states. Because of Pauli exclusion, the only strings of operators that can survive in the matrix elements for legal fermion states are those in which all of these operators here in this list are all different from one another. That is, they correspond to annihilation operators for different single particle states. And each of them is different from both of this and this, because these have to be different states again from any of the ones in this list. Since otherwise we would be trying either to annihilate two fermions from the same state or create two fermions in the same state. Hence, for these states, since no two states in the string of creation operators or in the string of annihilation operators can be identical, not only do the pairs of annihilation operators anti-commute and the pairs of creation operators anti-commute as usual, so also do the pairs of creation and annihilation operators with different subscripts, other than possibly this one pair here. Hence, in this overall expression we'd written down before, we can swap the creation operator be a dagger all the way from the left until we get to the left of the corresponding annihilation operator be a over here. And as we do that, we will only acquire minus signs as we do those various swaps. Actually, we acquire an even number of minus signs because the number of swaps taken to get to the middle is equal to the number of swaps to get from the middle to the final position because of the symmetry of that list. So there is no change in sign in all of these swaps, and we can repeat this procedure for each creation operator other than this specific one here, which we do not need to move anyway. Hence, with all these swaps, we can rewrite this expression for our operator as this one here, where we've managed to move all these operators, group them side by side over here, except for these two, which we haven't moved. Or more simply, we can just note that these are the number operators for each of these possible states here. When this operator operates on a specific n-fermion basis state, the only terms in the summation that can survive are those for which the list of states, a, b, up to n, corresponds to the occupied states in this particular state we'd chosen here. And so the sum over a and b and so on, all the way up to n, omitting both I1 and I2 out of that list, and the number operators, can be dropped without changing any matrix element. Hence, we can write this simplified version. This operator is going to have the same matrix elements for any possible states as the previous one we had written down. It makes no difference here which fermion we are considering. This integral turns out to be the same thing, this number here. And so the sum over I is trivial here. It just sums n times what we have here. And so the sum over I and the 1 over n cancel, and we're left with this expression for our operator in this new formalism. And we've also further simplified our notation here by substituting j for I1 and k for I2. This is the general form for a single particle fermion operator. You see it has an annihilation operator for state k here, a creation operator for state j there, a number that is related to the states j and k that we can work out as an integral, and we formally sum over the states j and k. The Hamiltonian that we looked at before is just a special case for a diagonal operator, that is an operator that's expressed on its own eigenfunctions, and then all the off-diagonal terms disappear because all of these off-diagonal, that is of the j not equal to k, integrals here would disappear. Hence, we find a very simple form for the single particle fermion operator, valid for any number of fermions. That's the point. This will work no matter how many fermions we're talking about in the system.